First Spin. Welcome to First Spin, a show where I learn how to use the Parallax Propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of two experts.
I'm Whisker, and we also have Mr. Roy Eltham.
Hello.
And
Hi,
Roy's the
Roy.
real sort of expert. I've done quite a bit with these things, but Roy's sort of the guru around here.
So, last week we talked about cogs and interrupts, kind of a overview, I would say, of the propeller chip, right?
Pretty much.
Okay. So I thought today it would be very, very appropriate if we were to go through the pins on the chip, because there are a lot of acronyms and probably a lot of things I don't understand about them. So, if that's okay with you guys.
That sounds great.
Yeah, there's a lot of interesting stuff about the pins, actually.
Okay. So the first one, pin name, P0 to P31. And these are the I/O pins, input and output, I believe.
Correct.
Okay. And the description, they are general purpose I/O port A. Any significance to the port A?
Yeah, there's internally in the propeller, there's two sets of ports, register ports for the I/O pins, although the second set are not connected externally. That was going to be in a future chip that they come out with.
So it's going to be like a extra group of pins that people would be able to address, or?
Right. So there would be pins 32 through 63, which is the second 64 or second 32 pins, and those are port B.
I see. Okay.
But there is no chip with those on them.
It's kind of like
Oh.
the Matrix. There is no port B.
Cool. Okay, it's the mystery sibling. Got it. Okay, so these can source or sink 30 milliamps each at 3.3 volts DC.
Although it's 40 milliamps. Maybe your book is
My book
out of
might
date.
be a little older. I think it's like version 1.0.
Right.
Yeah.
So the updated manual says 40 milliamps for each,
Okay.
which is the correct data.
So source and sink, that means it can output or take 40 milliamps each. So all of these pins can each take that much at 3.3 volts DC.
Probably not all at the same time, though.
Correct.
Okay. And
Any individual one can source or sink 40 milliamps. If you source or sink multiple pins at 40 milliamps, you will overload the chip, though.
well, okay, so let me ask then. If you have like half the pins sourcing and half the pins sinking, does that equal net zero? And does that mean that actually works, or is it like total, like a absolute value of the current can't be more than whatever the number is?
Well, realize half your problem there is heat. So current going through the chip causes heat. The more heat,
Oh,
the hotter it gets, the more trouble you're going to run into. So that's
So-
part of the problem.
so the safer thing would be to say that total. And okay, so the next line here is do not exceed 100 milliamps source or sink total across any group of I/O pins at once. So I'm going to go by that 100 milliamps. So if we have, actually, is that different now, Roy?
Nope.
No, it's the 100 milliamps is the max.
I'm trying to get to the same exact page you are.
Okay.
And the problem is that my manual is newer than yours, so...
Well, you
it
can tell
doesn't-
us the newer stuff.
So
'cause,
they
I
have
mean,
the manual up on their website now?
They do.
Okay.
Yes.
Yep.
We actually have a paper
Hard
copy.
Yep. Good old version 1.0. So is it absolute value, or is it just like net value?
I don't know about the does source opposite sink negate it. I
Okay.
don't think so, but
Okay.
that's getting into more of the electronics side of it, which is not where I'm more of an expert. I'm more of an expert on the programming side.
Sure. I have stumped the experts. Yes.
Well, my answer on that would be that not only is that probably not going to help, it's probably going to be even worse because you're essentially doubling the heat by going both directions at the same time. It's probably not going to. It's probably going to brown out, honestly.
Okay.
Yeah, it's most likely not going to be a good idea to go over either direction, sinking on some and sourcing on others, to go beyond the 100 or whatever value.
So the real answer to your question here is not whether or not the pins can do it. It's more along the lines of they're not designed to do that kind of thing. They are I/O pins. They are not like power transistors or Darlington arrays or something like that. You would use them to control something that can switch larger currents and larger voltages.
Okay. And also then let me also ask, so each pin does not have to have the 30 milliamps. It could have like 10 milliamps.
Or even less.
I see. Okay. Well, that's not a problem then.
So you're coming from electronics approaching this thing.
Yeah, kind of.
So you can very much understand what we mean when we say you would use a tiny bit of current off of one of these pins to control a transistor that is switching a larger current source.
Yep.
And then, the problem is gone.
I get it. Okay, I get that. I will err on the side of safety. How about that?
Correct. That's the best plan.
Okay. Logic threshold is 1/2 VDD or 1.65 VDC at 3.3 VDC. So I'm going to take this to read that if the pin is to read high, the signal going to it or coming from it has to be at least 1.65 volts DC, given a 3.3 volt DC power supply.
Right. So on input, when the signal crosses over the half VDD level, which in this case would be 1.65 volts DC, then the pin will read as high if it's above. And if it's below 1.65, then the pin will read as low.
Got it. Okay.
And when you're outputting, the chip has a specification in the data sheet of when it's outputting low, it's below some certain value of voltage, and then if it's outputting high, it's above some certain value. And those are different because it's just what the chip is spec'd at.
Okay. And can you set...
I have one detail there before you get any further along.
Oh, sure.
When you're doing it as an input and you put it into what I would think of as a high Z situation where that pin isn't like actually connected to anything, it's just floating, the voltage will float around on it in a sort of virtual way, and you'll get really interesting and strange. It'll go high, go low, go high, stay high, go low. It'll jump all over the map. So usually you would use either a pull down resistor or a pull up resistor to lock the pin into one or the other, and then your input is powerful enough to overwhelm that and push it past the threshold in the other direction. Does that make sense?
I'd have to study pull down and pull up resistors a bit more, but does that mean you have a resistor going to every pin?
The ones that you're using as an input, you would have like a resistor going to ground would be a pull down. And then you have your input is a voltage that's coming in that isn't necessarily on a resistor. So normally, if that input is low, the pin is going to be pulled down to ground, and it's going to think it's, a zero.
Yeah.
But when you turn a voltage on, that voltage is going to see the pin as a better place to go than through the resistance down to ground. So it's going to easily see that as a high, a 1.
Right.
Okay,
and the pull-up resistor is the opposite. You're hooking the pull-up resistor to your power rail, and that holds it high until an input pulls it down really hard to ground.
How can an input pull it down to ground?
If you directly connect the pin to ground,
Say your
that's
input
gonna
was
be,
a switch, and this other side of the switch was attached to ground. So your pull-up resistor is connected through a resistor to the power rail, but your switch is connected just straight off to ground. It's going to read high until you flip that switch, and then that no resistance line is going to very much overwhelm things, and it's going to read low, super low.
I gotta think about that real quick.
Yeah, once you get your head wrapped around how it works, you're like, oh yeah, I get it.
So it pulls it high, but if you want it to get turned off, you give it a way to get to ground, which is through a switch.
which has less resistance than your pull-up resistor. You typically use a very high ohm pull-up resistor so that it's a weak pull-up, so that any other lower resistance signal will be able to pull it down, or vice versa. You have a really high resistor going to ground, and any weaker resistance that goes high will pull it high.
So can you guys give me an example, like a hobby example, I guess, of when you would use a pull up versus a pull down?
Well, Whisker just gave you one with a switch, right? If you have a normally closed switch, then it's going to be connected to ground all the time, and you want to have your pull-up resistor on there, so that when you release the switch, it will open the connection, and your resistor will pull the signal high, because there's no longer a connection directly to ground. Whereas if you have a normally closed switch, or normally open switch, sorry, I said normally closed a second ago, a normally open switch, then it's not connected to ground, and you want to pull it down so that it reads down as off, and then you push the switch and it connects it to ground. I'm sorry, connects it to high. I had it right in my head, but I said it wrong.
It's not the sort of thing that's easy to sort of explain just like in a big long string of text. But I do have a real world example for you that you actually do have some experience with. All right, I took a Hammond organ, and I wanted to hack its keyboard so that I could use the keyboard to input a whole bunch of on and offs into a propeller.
Yeah.
Now, it has a whole lot of keys, more than 32. So,
yeah.
I had to use an I/O extension system using shift registers. But the input pins on those shift registers work just like the input pins that you're talking about on the prop. So the same thing applies here. For every single one of those keys, when you push it down, it connects it to a power rail.
Okay.
I applied 3.3 volts low current to that power rail.
Okay.
So now whenever I push down a key, the output wire of that key, the switch is closed, it's on, it's giving 3.3 volts. And that's attached to one of my input pins.
Okay.
That input pin is connected through a high ohm resistor to ground. So if the key is not pressed, that pin is only connected to the circuit through the resistor to ground.
So, okay.
And when I press the key, it closes, and now that pin is connected to ground, and it's also connected to the 3.3 volt power rail without any resistors. So how do electrons choose which way they're going to go?
Path of least resistance.
Path of least resistance. It's all about the resistance.
So if you pull down, it's a default off. If you pull up, it's a default on.
There you go.
Right.
She's got it.
Exactly.
I just explained it in like 4 words. Oh, yeah.
Yeah, but the science behind it is also very important.
Okay. We will. I'm gonna have to re-listen to this. All right. So then it says here. So that's now okay. So when you we'll go into that further. Here, the pins shown below have a special purpose upon power up / reset, but are general purpose I/O afterwards. So we have P28, P29, and these are I2C connections to optional external EEPROM. So I2C, what's that stand for?
It's integrated circuit to integrated circuit. It's the I2 is actually a squared, so it's I
squared C.
IC. It's inter-integrated circuit communication. I believe that's what it stands for.
Okay.
And so it's a serial communication between two chips.
Okay.
In this case, the EEPROM chip.
Okay.
And the SCL there is the clock pin, and the SDA is the data pin.
Okay.
So what happens is when you boot up the propeller, if you are not connected to the serial port, which is the next two pins in that description there, it reads the EEPROM through the I2C port. Through those two pins, it checks to see if there's an EEPROM there, and by sending out signals on those pins, and tries to read the EEPROM data into its hub memory.
Okay. And so this clock, this SCL, the serial clock connection, that provides, I guess, a time, like a tempo, kind of like in a song, a tempo for the EEPROM to write its stuff to the system too.
So for each bit of data, it clocks the clock pin down and up, right? Up and down for each serial pin coming off the data line.
And it doesn't necessarily, these kinds of things don't necessarily have to be a regular tempo. It's a little bit like, do you remember that game that we would play as kids, the red light, green light?
Yeah.
The clock pin is like the light. So you turn it on and an event happens.
Okay.
Now it's predetermined how long that event's going to be. It's usually, just a single bit is being moved around. And then it turns red or off. Turns on, another bit. Turns off. Now, the way that this works is that it turns on and the other one knows to either turn on or off its pin when that happens.
Okay.
Just very simple serial communication.
Okay.
Right.
You're using one to say time to talk, and then the talking happens on the other pin. Time to talk again, something else happens on that pin.
Okay, so P28 says time to talk, EEPROM, I allow you to talk, and then P29
is where the talking is happening in.
Is like, oh, okay, we got the okay to talk, so now we're gonna talk.
Yeah, and that happens one bit at a time. So pin 29 will just be high or low.
Okay.
For some predetermined amount of time after you do the clocking sequence. And the protocol for I2C is actually very complex, and there's a whole sequence of sending out the appropriate signals to the EEPROM to make it be the one that you're actually talking to, because you can have multiple devices hooked up to an I2C bus, all on the same two pins.
So there's a whole bunch of complicated stuff there, but the way in which they set it up, it's very simple for us users. Because, like Roy said, if you're not connected on the serial cable to the prop, then it defaults to using the EEPROM. It turns on, it says, I'm going to try to download a program from the EEPROM.
Yeah.
And then just does its thing automatically, because that's a built-in thing that the prop knows how to do.
Okay.
Right.
Okay.
And then the next two pins, pins 30 and 31, are connected to your USB port through a chip that does the serial communication with USB. And what happens with that is when the propeller first turns on, it first tries to communicate over the serial port with the host computer. And if you have your prop tool running, and you're downloading a program at that point, it will then receive the program directly through the USB port instead of using the EEPROM.
Right. So that's like if you're writing to the RAM.
Right. So when you use the prop tool to download into the propeller, what actually happens is that it resets the propeller right at the beginning, and the propeller sends back a code over the serial port, and then the prop tool sends back a code to the propeller to say, okay, I'm going to send you a program now, and then it sends the program down, and the propeller accepts it, and then either just runs it or stores it in the EEPROM.
Right.
It's very simple and beautiful, isn't it?
Right, it's awesome.
So then, okay, so say you're writing to the EEPROM, right? But you're writing from your computer. So then does it, and P31 is the serial receive from host, so I'm guessing the receive from the computer. So your computer, you want to write it to EEPROM, so the data or whatever goes from your computer through pin 31 and makes its way to P28 and P29?
Well, it's a little bit more delayed than that. What happens is the whole program gets downloaded into the RAM of the Propeller.
Okay.
Through pins 30 and 31.
Okay.
Through communication. And then once it's in there, it gets copied out pins 28 and 29 into the EEPROM.
I see.
And that there's codes when it first communicates with the Propeller, when it's right after the reset. Like I said, the Propeller sends a code out, and then the prop tool sends a code back down to it. There's multiple codes it can send, and one of them is to program the EEPROM with data. And you send down the code, and then it sends it out to the EEPROM. Another one is just run this program. Mm-hmm. So you send down the code, and it runs it.
Okay.
So, Eddie, you can see that the normal way that we do it is, programming it through the prop tool. But there's absolutely nothing stopping somebody from making, say, one prop that is smart and has a little serial connection on it to be able to plug into a project that has a prop as its main, processor, and automatically give that product that has the prop in it a firmware update without having to hook it up to any computers whatsoever. You could make your own dedicated little prop thing that people could plug into their projects and automatically do a EEPROM firmware upgrade.
Right. There's also some members on the Parallax forums that have built multiple prop boards that have 2 or 3 props on them, and they're set up such that one of the props can program the other props.
So he boots up and he downloads his program because he's attached to an EEPROM. The other ones boot up and they think they're attached to an EEPROM. They're actually attached to a couple of pins on the leader. And he goes, "Oh yeah, I'm an EEPROM. Here's your program, dude." It's awesome.
So those are fairly advanced topics that we can worry about way down the line for you. But
it's important to know that it's possible, though.
Right.
Okay.
Because you obviously understood how it worked because of the question you asked about how it comes in through 2 pins and goes out the other 2. Mm-hmm. Yeah. And that's all these advanced things are doing. Same thing.
Okay.
Right.
Cool. Let me see. Let me make sure I don't have any other questions about those. Okay. So VDD is just the power rail voltage, and it's 3.3 volt power, but you can use 2.7 to 3.3 volts DC.
Right. So it just allows it to be tolerant to using it, like, say, with a battery that eventually will go below 3.3 volts down a little bit, but the processor will still work.
Okay, gotcha. And then VSS is ground. That's fine. And then BOEN.
Okay. So that's brownout enable.
Yep.
And the little N there means active low.
Okay.
Which means that it will be enabled if the pin is held low.
Okay. So you would want to, based on what we talked about earlier with the resistors, you would want to do a resistor or pull down resistor.
Well, you don't have to use a pull down resistor if you don't want to be able to pull it back up. So in the case of brownout enable, usually you just tie it directly to ground in order to enable it.
Okay.
Because you don't want to dynamically turn it off and on in most cases. If you want to be able to turn it off and on, then you would use a pull down or pull up and have a switch that would turn it off and on.
Okay.
But
And explain to me what brownout means.
That means that the power goes below the threshold of what the processor is capable of running correctly on. So the reason you would want to have brownout detection is to avoid running the processor with too little power, and when it does that, it would perform erratically and be unstable. So like you might have, important hardware hooked up to it that if it were browned out, it might send the wrong signals out the IO pins and run the incorrect code and cause all kinds of problems.
Okay.
So the brownout detection code causes the chip to, if it detects that it's got too little power to work stably, it goes into reset mode and holds itself in reset mode so that it's not running any program. And all the pins are set up to be inputs, which makes them float so that they aren't driving any of the output pins to cause problems. And that's important. That's fairly important. If you have a delicate piece of hardware plugged into the IO pins, that if you send it the wrong signals, it might break it or cause it to do, damage to the product that you have the propeller in.
Okay, so let me just clarify. If you have this enabled, which means that you have it
grounded,
connected through to ground, and say your voltage goes less than the 2.7 to 3.3 that the chip is required to run on. So say it's like 2 volts. All of a sudden, bam, you're in California, you got a brownout thing going on, and because you guys do have that sometimes. And 2 volts, and your chip senses this, then it floats all of the pins.
The IO pins.
The IO pins, so that nothing can go in or out.
No, it's not so nothing going out. It's just so that it is not driving any pins to be high or low. They will go into whatever state is connected. So if they're all like pulled high or pulled low by external resistors or devices, they will go to those default states. The chip won't be driving them to any state.
I see.
It's a safety precaution in case, like I said, you have something, important plugged in and you don't want the signal to become, driven erratically by the processor doing unstable things at low power.
Okay.
And so it holds it in a reset state so that it's not doing anything also.
That makes sense.
The last thing you want to have happen is, for power to dip, your RAM in your project to go a little bit funky, and, it's controlling some big industrial robot. And when it, gets back to doing what it was doing, it thinks it's somewhere that it wasn't.
Yeah.
And then it ends up, pushing a welding head through the metal that it was supposed to be working on or something.
Sure.
So instead, you've got this brownout protection system so that it can know if there was a power problem.
So why would you not want to use this?
You do.
You always want to use it. It's just,
but you want to have the option not to.
But yeah, it's an optional feature. I personally can't think of any situation where you wouldn't want this enabled, but I'm sure that there are people out there that have reasons for wanting it to not be enabled. To maybe they have their own separate brownout circuitry on the board that they've done themselves that they handle that.
Okay.
Something along those lines.
Okay.
Or maybe they want their brownout threshold to be even higher than what's stock on the chip.
That's also possibly true, yeah.
Do you program that, or
if you were designing for specs where you needed your brownout, threshold to be a higher quality of voltage that had to be applied, then the onboard thing is static. It's set to something.
Yeah.
And you want this, you just simply disable that brownout pin, design your own brownout circuit, on your board so that you could meet your spec for what your design needs.
I see.
Right. So like you might have a device plugged into the propeller that has to have 3 volts. Can't go down to 2.7 like the propeller can.
Sure.
So you would set up your brownout circuit to trip the reset at 3 volts instead of at 2.7.
I see.
So we're pretty much out of time for today. We got to cover a bunch of the pins, and we will be continuing on that next week. I'm sure Addie has questions about the XO and XI pins.
Yep.
Because those are like hugs and kisses? No.
Bad.
Okay, so thank you for listening. You can find this show every week on Tuesdays
Yep.
at FirstSpin.tv. Don't forget to subscribe with your iTunes or phone or whatever you use to get your podcasts. We very much appreciate it. And thank you to Ken Gracie and Parallax for stepping up and doing the whole sponsorship thing of the show. That's exciting.
Thanks.
Yeah, it's a really cool idea.
All right, we hope you guys enjoyed this, and we will see you all next week.
Bye.
Bye.
Bye.